European options are usually computed in markets under the assumption of Black and Scholes model. However, this kind of models present two major flaws: constant implied volatility and log normally distributed interest rates. This kind of behavior is opposite to the one observed on the market, where we see volatility smiles and negative interest rates. We present two alternative ways to reproduce market smile and skews, and show their usefulness in pricing structured products, in particular for nonlinear payoffs.
The first model we implemented is the stochastic alpha-beta model, for which the dynamics of the forward and the volatility are correlated. In particular, we analyze the stochastic normal model for European swaptions, since it's the one that allows negative rates. The big advantage of such a model is that it admits closed formulas for volatilities that allow us to calibrate model parameters by minimizing the sum of square difference of implied normal black volatilities with respect to the cold market bands. More importantly, we can calibrate parameters via normalized volatilities, implementing a calibration cascade. We calibrate first a reduced set of parameters on normalized volatilities, and then use at-the-money volatilities to compute the remaining parameter. This type of calibration is computationally convenient, since the first set of calibrated parameters is fixed for a long period of time, whilst the second can be updated regularly, since it changes with the at-the-money volatilities.
The second model is an additive model in a Besozzi setting. The fundamental idea is that we consider a forward price that follows an arithmetic Barnum motion with normal volatility, allowing not only negative interest rates, but negative prices. Reason why Besozzi models are so popular in fixed income markets. For the model, closed formulas are available for pricing and so for calibration. As for the sub-model, we implement both a direct calibration and a calibration cascade.
The sub-model shows computational advantages, taking a fraction of the time needed by the additive model to calibrate. In addition, it reproduces far better volatility smiles and skews, especially for far-from-the-money options, as shown for a 10-year tenor surface.
To test these two models, we price a certificate with a quadratic payoff, which we approximate via CMS couplets. The importance of using an appropriate model to price this kind of certificate lies on the fact that we have a convexity correction in the CMS couplet price, which is essentially a quadratic payoff. So it takes most of its value deeply far from the money, making this term very sensitive to skews and smiles, and that's why the black model is not effective in CMS pricing.
In conclusion, both models prove to be very useful in computing this kind of certificate. Indeed, having a stochastic volatility model allows us to reproduce volatility smiles and skews for any maturity and tenor. Moreover, closed formulas provided by this model can be applied to compute volatilities for any type of strike.